So today, so this is like chapter 9, which I loosely titled I want to start with the notion of this is getting close to like a big part of my own research area is I study a lot of notion of integrality and then closure. So what is this all about? Well, integrality is to, and I'm going to restrict myself mostly to talk about integral domains because it'll make the proof of some of this a little bit easier. Integrality is to integral domains as algebraic is to fields, right? So when we talk about extensions of fields, F is algebraic over K if every element of F is the root of some non-zero polynomial K, right? That's the notion of algebraic. How does integral fit in? Well, you have to tweak it a little bit to make this make sense. And at first, the first time I ever saw this, I thought, well, this is kind of arbitrary, right? But it turns out it's really not. So a lot of this stuff is kind of on the boundary, what I would consider the boundary of algebraic number field theory, algebra. Let me start off with the definition of this analog. I kind of said that the notion of integral is domains, algebraic is fields. So here's what it is. R side T be integral domains. We say that T and T is an integral. Here, T is a root of some monic polynomial x to the n plus r n minus 1 n minus 1 r1 x plus r0 x. You could actually use this definition for the definition of algebraic. In fact, in a lot of places when we talked about, the notion of algebraic stuff, sometimes I did say monopolynomial. And the reason is because if I had any polynomial over a field, and it's of degree, say, n, you can divide out by its leading coefficient, right? Because you're in a field and the leading coefficient is not zero, you can invert it. So in that sense, any polynomial over a field can be construed as mono, right? But here, what do we know about algebraic elements, right? One of the big things is, if you look at, so suppose F is not algebraic necessarily, the collection of elements of F that are algebraic over K actually forms the field, right? The algebraic closure of K in the field F, right? I'm kind of hoping something similar here is true, right? That integral elements form a nice intermediate domain, and in fact they do. Now, why do you suppose Mnemonic is important. That's exactly right. That's exactly right. So, so. So here's what I'm saying. What are the elements of Q that are integral? Well, this first one, they are any elements. The elements of Z itself. No. No. Certainly mnemonic polynomial coefficients. Z. So from this observation, we know that I like this definition. All elements of R are equal. Correct. Using the same trick, they're all roots of mnemonic polynomial exponents. Now, next question is, are there any more? Well, this is why mnemonic is probably needed. One of the reasons, as was observed, notice that every element of Q is the root of some polynomial. Like if but this is not necessarily mine. Right? But you think the one really technically minus one, you could adjust it. So we know we've got all Z. We know that. Okay. What rational numbers reach mnemonic polynomial? My claim is that's it. Just see. Yes. And let's assume since unique factorization domains, we can assume that the top and the bottom are factors. Okay. Let's say A over B. X n m sub n minus one x n minus one plus m one x plus c zero. With the mi's all in. Okay, so right now things. So we've got that. Well, this confuses my piece of the brain because I hate fractions. So why don't we clear this denominator? Notice if I multiply both sides by b and n, that'll do what I want to do. We'll clear out all the denominator. By the way, what conclusion? So suppose that we've got our element a over b. Right, a over b is equal to q. What conclusion do you want to come to about a over b? What do you think? B must be one. B needs to be one, right? That's what I hope. So let's do this. Let P suppose you have P prime factor that divides B. Well, if P divides B, it divides this entire mess. And it certainly divides 0. So P divides A again. That's so P divides A because P is a prime. So any prime dividing B must divide A. What conclusion must we come to? Notice as GCD of A and B is 1, no prime can divide B. And if no prime divides B, then this implies B is equal to, there are only 2 integers that are divisible by no primes. And minus one, which implies A over B is. So after all this rigmarole, we've shown that every element of Q that is integral over Z is already in Z. Everybody agree with that? Anybody want to generalize what we did? What do we use about Z that's specific to Z? What are the properties of Z that we had to use to make this flow? So, right, but what is it about Z that makes all that work? Well, actually, you gave the best answer. Naively, you could say what it is about Z is a UFD. So for a UFD, this is true that if you have any UFD with this quotient field K, then all the elements in the quotient field that are integral are already in the UFD. But you're right, actually, this is also true for any domain where any pair of elements has a GCD. It's true. Okay, any questions on that? Let's look at a couple more examples. Here R and T and R is a field. Then T and T is integral of R if and only if T is certainly integral always applies algebraic, and the converse is true just because you can divide out by the leading coefficient of whatever the polynomial is for T. Here's another example. Every element of Z is joined with the square root of -5. Actually, I'll double up on this. I'll demonstrate this very quickly. A typical element of sample looks like integer plus integer times right. We see that here all the time. It's squared minus 2x plus polynomial, which is that's easy to check. Notice you see some things more we talk about superatomic because that coefficient of the x term is minus the trace of that, and constant term is the norm of that. Here's another. This is integral over Z, right? It's the same sort. What makes this interesting and what contrasts this, even though I didn't say this over here, the quotient field of this is Q adjoining the square root of -5. Right? All right, just change these into fraction numbers. That's the quotient field of this. this ring is everything in the quotient field. Q radical 5 is integral of this. For this example over here, it's not enough. Can anybody name an element of blank Q minus -3? Over Z. But not in C equals square root. Let's say maybe if you all put your heads together in unity, you might find such things. You might see it later. Take a rational number plus another rational number square root of -3, and make something that's equal to Z. One. That's from the cube root mean. So this sound. I mean, this is like really, this is e to the 2 pi. So when you cube it, you get 1. And actually, it's irreducible. Actually, you can check this one out rather easily. So notice this one here, everything in here is integral, but there's other things in the quotient field that are integral here. This is actually, I bring this example up because this bifurcates the quadratic case. So here's an exercise just for fun. Exercise. Suppose D is a square root integer. Um, set of elements in Q going to the square root of A that are integral of Z set of elements is exactly Z adjoining the square root of D. You know, D equivalent to 3 and C adjoining 1 plus square root of D. Yeah, D. 1. Checking in these conditions that this works out is not too bad. Checking that these are exactly, that is, if there's nothing else beyond this, is a little bit more involved. B is equivalent to 1 mod 4 is a special case because if you take a norm of this element, that is, if you multiply it by its conjugate, what you get is 1 minus D over 4. And of course, 1 minus D over 4 just means 1 minus D is by 4. That's special. Okay, any questions? By the way, like I said earlier, I'm kind of hoping, I was sort of pulling for integral elements to form some kind of like structure, a ring. I would hope that the sum of 2 integral elements is integral to the product of 2 elements. But, you know, just because some Yahoo over here says it's root of monic polynomial and this is root of this other one, how do you know that the sum of the product, right? This is very much like the algebraic conundrum. And if I remember, how did we show the sum and product of 2 algebraic elements were algebraic? We showed that adjoining an algebraic, a single algebraic element to a field made a finite extension. So you took alpha and beta, you adjoin alpha to F and beta to F, that's a finite extension. And we already did that finite extension is algebraic, so people algebra. There's the same thing, but it's more intricate with domains. So let me give you the theorem and then we'll worry about how to go about it. I don't know why the rock costs money. This should be a theorem, not a theorem. This theorem can be expressed in more generality than I'm going to do it. I'm going to restrict the case to domains, but R and T be domains. And U an element of a bigger domain. The following are equivalent. Number 1, U is integral over R. So it's the root of some monic polynomial coefficients in R. 2, there's a finitely generated R submodule A and T. Such that UA is this is really this condition because finding if something is the root of a polynomial, that can be potentially a lot of work. I can know that an element is integral, but finding its polynomial can be computationally very expensive. It's not always clear how to go about it. There'd be, you know, if you were just completely naive about it, there'd be like terrible in your mouth. This other one says the other condition, which is equivalent to integrality, just says, hey, I can find some finitely generated submodule of T such that U times A still contains. That is super. One of these directions is decidedly easier than the other. So suppose that your integral okay, so suppose that U is where of course all R is R. Suppose the U is the root of this, right? Well, let's look at where this n is indeed the same as this. Notice that A is finally generated because that's the way I made it, right? There's only n generators here. A is certainly a submodule of T, because in fact U is in T, so every power of U is in T. Now, if you look, and this, my friends, folks, uh, so notice everything in here, every one of these generators corresponds to one of these generators, with the exception of U to the N. The U to the N can be expressed as a linear combination. So in particular, if U is a root, then we've got the UA is contained in that. Basically, the key here is that the nth power of U can be expressed as the lower powers. So inductively, every power can be expressed as the lower powers. Am I okay with that? Of course, the interesting direction is heaven. Right? I mean, having this seemingly simpler condition used in the field, that is, there's a finitely generated submodule, R submodule of T, such as UA is an A. How does that give me that there's a harmonic polynomial? And this is really cool. Let's do two plus. Suppose that A is generated by A1, A2, maybe 3. Now, we have the UA is in A. This means when I multiply U, in particular, if I multiply U by any generator, say UA1, that's still an element of A. And so it can be expressed as a linear combination of A's. Right? Let me, in general, say, if you look at UAI, or this is an arbitrary one of these things, what do I know about this animal? Well, UAI is still an A, so it should be written as a linear combination of all the naked A's here. So it's lambda IJ, AJ. J equals 1 to N. Everybody okay with that? Now, this will be a fun blast for everybody. Let me see if I can write this down right. Well, oh, and here, of course. Let's call this polar IJ. Let me see if I can get this right. I can write this as a matrix equation. Let me take a quick gander to make sure this is all working out the way I want it to. Yeah, it looks like it's working out the way I want it to. So this matrix represents this side, right? If you take matrix made by these times that column vector A1 to AJ, and the corresponding what does that mean about you? You, you is an iodide, that matrix. So. I'll look. You, a root of one or two times. Harmonic polynomial. We have coefficients. Take term, but you get money. Well, up to a sign, which is easily fixed. Okay. Any questions on that? I think that's like a super friggin' characterization here. Okay, so let's make some hay with this. So here is a very nice application of this. Theorem 915. What are inside TP domains? If U and V are integral over R, then okay. You know, this reminds me back to the days when we were talking about fields. Sums of products algebraic, elements are algebraic. Good luck finding the polynomial. Even if I give you the data, I'll tell you what the polynomial for U and V are. Good luck with that. Let's suppose that A and B are the finite generating modules. A, B, C are finitely generated. Are modules. Such that, let's say that UA is an A and BB is B. Note that since these are submodules of T and T has a range structure, the module A times B makes sense. It's also a finitely generated R module. In fact, all you have to do is take all the generators of A, all the generators of B, and look at all the separate products that you get when it generates there. So if this is generated by N elements and it's by M, then the whole thing will be generated by no more than N elements. This is an easy calculation to do. I encourage you to do this, but there's your finitely generated module. Hence, sums and products are integral elements of integral. So let's look at this corollary. 916. If R and T are domains, then the integral closure of R and T is a subring of R and T. So the collection of elements in T that are integral over R is a domain, is a subring of T. I would call this sometimes the integral function. And this follows immediately from this because the elements of R bar T are closed under addition and multiplication, so it's a subring. Okay, any questions? Okay, so with regard to this notion of integral closure, right, the set of elements in the big ring that are integral over small. Let me throw some terminology at you. Definition 7. Suppose that R inside T are domains. And RT, your closure of RT. we say that. If the integral closure of R and T is just R, it's gonna be at least R, that's all it is. We say R is integrally closed to T. If the other extreme, right, because it's always separating T, if the integral closure of all of T is all of T, we say T is integral over R. There's a very important special case of this. Yeah, in the special case where T is the quotient field of R, then the integral closure of R in its quotient field is called the integral closure. So if I say the integral closure of R without saying in some other ring, just naked integral closure, that means implicitly that it's the integral closure in its quotient. This is different than algebraic closure. Algebraic closure usually goes to much larger fields. Integral closure, you're always confined to the quotient field. If in this case here, if R is equal to its integral closure, we say R is closed. Actually, integrally closed, surprisingly, it seems like something that I just kind of made up so that I can definition for your notes. But integrally closed domains actually it still astounds me sometimes how much nicer they are and what nice properties that you get from them. We're going to get a nice characterization of integrally closed domains later, but I think this is good for the day. Any questions? All right. Well, I will see you folks on Wednesday.